All right, in the past couple videos, we talked about vaporization and some of the weird stuff that happens with that. We still need to talk about like melting and freezing and sublimation and deposition. We haven't talked about any of those yet. Those ones go by pretty quick, so we're gonna do both of those in this video. Okay, so melting is basically when you go from a solid to a liquid. Presumably you've heard of this. Now here's the confusing bit. It's still referred to as melting, but when we talk about enthalpy, it's not referred to as enthalpy of melting. Some idiot decided this should be called fusion. The confusing bit is that fusion is a chemistry word that we will learn about later in this semester when we talk about nuclear chemistry. So I hate this, but this is what all textbooks call it, and I can't fix that. Okay. So when we talk about enthalpy of fusion, all we're doing is talking about things going from the solid to the liquid phase. It's melting. Okay, so delta H of fusion, FUS. Okay. So for example, we looked at water in the last one, we'll look at water in this one. So basically water going from a solid to a liquid, ice melting, okay? The delta H of fusion is equal to positive 6.0 kilojoules per mole. What we're seeing is that it takes significantly less energy to make ice melt than it does to make water turn into steam. We saw that for the enthalpy of vaporization for water, it was like 44, I think. For this, it's only 6, which is why your ice cube, if you leave an ice cube sitting out on the table, it'll melt pretty quickly. If you leave a glass of water, it'll take forever for it to evaporate. It will eventually, but it takes a really long time. Okay, and the same type of calculations can be done like we did in the last couple videos. Okay, so where if we have 17 grams of this, we can calculate how much energy there is. Similarly, there is not a separate enthalpy of freezing. So even though melting has a weird term, freezing does not. So the delta H of freezing is essentially just the negative value of the delta H of fusion. Okay, really not a huge deal. Okay. When we talked about boiling point in the last video and the video before. Melting point is another thing we need to worry about here. Boiling point was a little complicated because as gases evaporate, temperature plays a huge impact on how easily things are going to boil. Melting point is a constant, okay? It's the temperature at which a solid melts. And this one is pretty constant, honestly. Okay. If you ever take organic chemistry, which a lot of you probably will, you can actually use this to identify. It's useful in like identification and purity of measurement of compounds. Okay. Okay. So it can be used to identify and determine the purity of solids. We do this a lot in organic chem labs. Like basically if you mix this reaction, isolate your stuff, filter it out, whatever, and you get this crystal. We want to know, did you do a good job? Is it pure? So what you do is you take it and you melt it and you measure what temperature it melted at. If it's really close to the expected melting point, you did a good job. It turns out that impurities, so if you have other stuff mixed in there, like stuff that didn't react right, or other side products, or just whatever, who knows what in there, it tends to lower the melting point a little bit and make the melting range a little broader. If you take organic chemistry, you'll get all the details on this, but we can actually use it to determine how pure your substance is. Okay. In the last video, we talked about supercritical fluids. There is a really weird thing that that melting and freezing does, something that I actually saw in my car this morning when I started it. I had a water bottle that I had left in there, and yeah. So this is something called the cooling curve, and we're going to do this for water. Why not? Okay, apparently water is our go-to example for this chapter. So what we're going to look at is just temperature versus time. So let's say 0 degrees Celsius is here. Okay, so this is the freezing point of water, just what you'd expect it to do. So it turns out that if you have a liquid and you're cooling it, what happens is, you know, it kind of steadily cools as time goes on, and you would expect that when it gets to 0, it will freeze. And it kind of does, but I'm going to leave a gap. So what you have right here is just pure liquid, and here you have liquid plus solid. Okay, and it will actually stay at 0 degrees until all of it melts if you're going up in temperature, or until all of it freezes, and then the temperature will drop. So if you have an ice bath, if you have just water and ice sitting together, it should be at exactly 0 degrees. Okay, because if it was warmer than that, the ice would have melted. If it was colder than that, the liquid would have froze. But it turns out that if you're really careful, we talked earlier about, a couple videos ago, about the shape of water and how as a liquid it goes like this, but as a solid it has to expand and line up those hydrogen bonds. It turns out that it takes a little bit of energy to make that happen. And as you're cooling it, you're depriving this of energy. So it's actually difficult for it to form these crystals if you don't have the right conditions. So what happens is there's this weird thing where it can actually get colder than freezing and still be all liquid. And if you add a little bit of energy, it will allow the crystals to lock into place and form ice, and then a solid will start forming. This is what happened in my car this morning. Basically, this one's not frozen, but you basically, if you have a water bottle and you leave it in your car, it'll look liquid, and if you take it and you tap it, it'll like start crystallizing all the way up through, because that tap added enough energy to get it up to the point where it could start forming crystals, where you could knock those water molecules apart so they could do this. But if you would have just left it, it would have stayed liquid until some amount of energy was added. This is called a supercooled liquid. It's not real useful, it's not real common, but honestly, if you have a water bottle and you leave it in your car and it's freezing conditions like it was this morning, you've probably experienced this even if you didn't know what was going on. But technically, you're kind of violating the expected rules of physics here. You actually have a liquid below the freezing point. When a liquid and a solid mixed, like water and ice, stays at 0, you can just have water that's technically below until you add a little bit of energy to bump it up there. Not a huge deal, not as useful as supercritical fluids, but I just wanted to point out that this weird thing exists. Okay. I really am not going to go, I'm only going to briefly mention sublimation. Okay. So, I guess page 11, try to keep things straight. So, sublimation is essentially when you go from a solid and you skip the liquid phase and you just go straight to a gas. CO2 does this, iodine does this. Iodine is these really pretty purple crystals, and usually they're kept in a sealed jar because it's, you know, pretty poisonous. And honestly, if you heat it up at all, those crystals will not form a liquid, but what will happen is you'll start seeing like these purple fumes coming off the side. Or if you ever have dry ice, that's solid CO2, it doesn't go to liquid CO2, it doesn't melt and then evaporate, it just literally skips that whole process and jumps straight from the solid to the gas. Okay. Well, we said that there was delta H of vaporization, there's delta H of fusion, there's also delta H of sublimation. So delta H of sublimation, you will almost never find a table for this, because it turns out that even though you're not going through the liquid phase, all it matters is where you start and where you end. So you get the same answer if you add up delta H of fusion plus delta H of vaporization. Okay, so, and then delta H of deposition, which is the opposite, is negative delta H of sublimation, just like we saw in the previous ones. So here's the idea, is rather than, you know, when we looked at our phase changes, there was freezing and melting, there was evaporation and condensation, and there was sublimation and deposition. I think that was the order, okay, which is 6 different things. But it turns out all of it can be summarized with these 2. Okay, so if you ever look these things up on a table, you're probably only going to find these 2 because the other 4 options can be derived from this. So if you look up the delta H of vaporization, the negative version of this will be the delta H of condensation. If you look up the delta H of fusion, the negative version of that will be the delta H of freezing. If you need sublimation, you just add those 2 values together. If you need deposition, you add them together and then make it negative. Okay, So really, we're not going to do much with sublimation, but it's not uncommon, but really we've kind of already covered the other two parts. We've laid the groundwork, so we're in pretty good shape here. Okay, thanks for a quick video.